All right, let's get started. Are there any questions about last time before we continue with Spark stuff? Good to know. Okay. All right. So we're going to continue with just some Spark exploration and how to express certain things that we want to do in Spark. So we covered briefly last week on Thursday row-wise operations and how they operate per row. So they can either eliminate the row, like filter would, or add new rows with explode, or add columns to a row or removing columns from rows. So we can take a look at another example here for, something like an aggregation, where the job of an aggregation is to combine multiple rows into a single row. Now, how this combining works will change depending on what the aggregation actually is, on what you're aggregating on. So an example of an aggregation would be a sum. So if you want to find the total of all of a numeric column, then the sum would be an aggregation. And what it would do is it would take all the values in the column that you're aggregating over and combine them into a single row. And that combination is just the add operator. And that idea is extensible to lots of different kinds of aggregations. You can also aggregate by key. So you can submit these aggregation functions over a subset of rows. So let's see here. If we pick up where we were leaving off last time, we should restart. We can input Spark. We're starting a local Spark session, so this isn't running on EMR this time around. And we're still working with the local Shakespeare dataset. All right, so that still works. That's good. Oh, is it still working? Good. Okay, so last time we covered the question of how are we going to find the most common word in this data set? And how we did that was we would take every line, because the initial state of this data frame is we only have one one line per row. What we want is we actually want one row per word. So what we could do was we could split every line on the white space. And then once we have that array of words as a column, we can use explode to expand it into lots of different rows that are independently managed. So now we have one row per word instead of one row per line. Everybody remember that we did this last week? Okay. Now we did some other munging to it. We also want to make everything lowercase, so we don't want it to be case sensitive, and we also want it to strip out punctuation and other stuff. We also, after all the punctuation and everything is stripped out, we don't want to count the empty string as a word, because it's not, it's just an empty string. So after we did that, we can do an aggregation on the word and see how many rows with that word appear. And that's our frequency. So this is an aggregation by key. The key is the word, and the aggregation is just the number of rows. We could do something else with it too. We could do something like, what is the total length of words that appear right after this word in a line? We could do something like that. And that would be a different aggregation. But the way we found the word with the highest frequency is we created a struct. And since we want both the word and the frequency, and we don't have to sort the entire data set, what we can do instead is we can create a composite data type built from both the frequency and the word, so that when we take the maximum, it will preserve both the frequency and the word in the result. Now, the way this max function works on a composite data type like a struct is it will go through the fields in order and sort by them in order, or take the maximum of them in order. So it will look at what the largest frequency is within the data set. If there are multiple words with the same frequency, it will use the word itself as a tiebreaker. Does that make sense?
Why would it's not just like you know, just for the living, you count all of them, or you need to have it like that.
You do not. So let's just copy this and go back over here. So let's say we remove this part and the group by, and we only had the count. That would give us just a single row. What just happened? Oh, it's called Willie in this one. Okay, so that gives us the total number of words in the data set. So you can definitely aggregate it just by just not by any particular key, but over the entire data set. So let's say we wanted to find like the lexicographically largest word, as in if you were to put all these words in alphabetical order, which would be the last one? You could do the max over the entire data set. As last word. Swagger. Wow. I don't even know what that means. Now I'm curious. This is Shakespeare. He does use quite a few unfamiliar words. Wait. It's not a word. He just made it up. What a boss. Okay. Bluster. Oh, that's funny. Okay. All right. So apparently the word doesn't exist, which is nice. Which is honestly what you'll usually find with words that are of a certain frequency. We could go with words that are of low frequency. That is just junk. So we could also use the same technique to find the word with the smallest with the lowest frequency. And what this will do is it will take the word with the lowest frequency, and the lowest frequency word is almost certainly 1. It almost certainly has a frequency of 1. There's some word somewhere in Shakespeare's data set that only occurs once. Let's see what that is. But what it will do is, since there are multiple words with a frequency of 1, it'll take probably the lexicographically first one, because that's the minimum, and that's what it will use. So let's see what that is. I'm curious, It's errands, and apparently that only happens once.
So what if you want like all of them?
So if you wanted all the minimums, then what you might have to do is 2 queries. So we could do something like word counts. Okay. That would be our table. And then we would have to find the min frequency. And that is start.table. Mag f.min frequency. I should just Easier to track. Naming things is hard. Okay. And what do we do after this? We can run a collect. And what collect does is it will take every row in this data frame and return all of it to local memory so you can work with it. Now, because we're doing an aggregation over the entire data set, this isn't inefficient at all because we're only using one row. We're only returning one row. So we can run a collect. And let's see what that is. Whoa. Yep. All right, let's see what we got back from min frequency, because that is certainly not just a number. Okay, so min frequency is actually, so then what we do is we do start table, counts, filter, call. Then we do a filter and we select everything. And let's say I want this alphabetically ordered because OCD that way. Okay, so these are all of the words that only appear once, and there's probably hundreds of them. But this is a list.
Okay, your meaning from PC. You did a min on the aggregates.
Yes.
So then you're return one, but you did it return data frame.
It did return a data frame. It returned a data frame with one row. So this returns a data frame with one row.
So we need to tell you this is mean frequency for 0 in the first row and the dot responding is in the column.
Yes. Yes. So this is called least, the column is called least common up here, and that's where this comes from. So it returns a data frame. You could do this collect with any data frame. So you could do it with the Shakespeare data set too. It's
So if you were just in such cells in that what will it not be in mean frequency in
no, because so if I did show, so we can try that. It will not return anything. Okay. So now we have the least common frequency is just one, and that's the value. But if we look at min frequency, that's just the null value.
Okay. Whatever after you put in the forces or Python to run, you have to know that the activity returns it. It has to be a Python action that actually goes to the some.
Well, yes, because this just tells it you need to take the data frame that's calling the function or that's calling this method and then display it. This method doesn't return anything, but Python is weird because even if a function doesn't return anything, you can still assign something to its return value. It's kind of alone in that. Like if you try to do this in Java, it wouldn't work because the return type for show would be void.
Whenever you put an option in there, but forces the pipeline to run, it runs the pipeline.
It does.
So even if show doesn't return something, the rest of this, right? Doesn't my expert table or my ag, those things return something once it runs. And I thought the show made it up.
So the show does make it run, but that value is immediately thrown away again because the data frame that you created by calling ag is not the same data frame as spark.table.wordcounts or spark table word counts. So the data frame that you get from this, from the result of this call and referencing the table, is not the same data frame as this column or as what you get after calling this method.
Right. Passing the law.
Yes.
The last action to force it to do the top part to assign it back to the top down. Right, you have, but it's assigned, you have an assigning operator. You want the whole thing assigned back to the frequency.
So the assignment operator, it assigns it to the return value of the last function that was returned in this chain.
Okay.
So the last function that returned in this chain is show. Show doesn't return anything. It doesn't matter what data frame you use. So this won't do anything. So you need the collect to actually transfer the contents of that data frame to your local instance or to your to the context that's actually declaring all of the Spark jobs. So that's what collect does. And you can use collect on, we can run this again, and you can use collect on any data frame, but just bear in mind that it will take the entire data frame and move it all to your machine, which means if you do this on a data frame with a billion rows, that will not work out well for you. So if you do something like this, you're going to want to take a limited sample. So, and how you can do that is you can do Spark table word counts dot limit. Let's say we want 100 rows or 10, and then we collect it. So when we do this collect, it's only going to collect the 10 rows because the data frame that was returned by this limit method only has 10 rows. Even if the data frame that called it has more than 10 rows. But the data frame that's returned with this reference and the data frame that's returned when we call limit are two different data frames. We can look at sample. Well, it keeps happening.
Jordan, for example, what if I want to determine my well, maybe like, what if I want to determine my subtemplate? Like, I can see the thing. I can do sample, get spark dot SQL, and I can use the select statement in there.
So you want a select statement in SQL?
The select statement in my, so I want to query my word paths to get my sim.
Okay.
So what am I using?
Are you asking for an equivalent SQL query to this?
How to be public? It's just, let's say instead of just limiting the term 10 random, I say I want all of them that start with it.
Oh, so you would do a filter.
Oh.
You would do a filter on the data frame. So we could do something like filter. Word. And then I forget the function. Let's see. Starts with. Oh. Okay, there it is. Okay. So we would have to do, it starts with. And starts with A. And then we could collect it with, which just happened. Letter name A. Oh, okay. That's what they mean. F dot little. So that's the confusing part about some of PySpark's APIs is this thing is supposed to be a column. This prefix argument is supposed to be a column, but I submitted a string literal. And what it's doing is it's trying to interpret the string literal as a column in the same way that it interprets this string new word as a column. So that's where that error came from. So if we look at it again, okay, and see all of these start with A. Now, so if we look at that error again, it says a column or function with a parameter name A cannot be resolved. Did you mean one of the following? And then it gives a list of existing columns. So this is supposed to be a column. What you can do is you can turn any Python literal into a column with this f.lit function. So that's what it's for. Now, if we did this in pure SQL, this wouldn't be an issue because SQL makes a syntactic difference between references to columns and string literals. So if we did this in SQL, like we could do it in pure SQL. Let's do it in pure SQL. Spark.sql. Then we can say select star from word counts where starts with the yeah. Okay. Now that should work. So this is the syntactic distinction. So it's covered by quotes. But that doesn't really exist when you're only using Python and you're not using Spark syntax. And you're not using Python syntax. Because either way, you're passing it in as a string. You're passing the column in as a string, the name of the column. So anyway, that is something that gets confusing sometimes when you're using Spark, is that sometimes these columns accept a literal and sometimes they accept a column, and it's weird. Questions on that?
So on that, your I've got call that when you go to physical to like or just structured or yep again. Is that just that function? Is that just returning all? And in order for me to reference a column and use a function?
Yeah, so usually. So if you use a column in isolation, or if you use a column alongside normal Python syntax, you need to reference it this way. But if you reference it using a PySpark function, and you don't usually have to do it that way. So the key difference here is when we had that other version of this query, where we had, f dot starts with, and we passed in new word. So that's a reference to a column, but we don't have to use f dot call because since this thing accepts a column as an input, it's going to interpret new word as a column anyway. But let's look at what happens with Python. Because with Python, the equals operator in Python is connected to this underscore underscore EQ underscore underscore function in Python. So what it does is many types in Python have a function defined for the equals operator. And what the column makes sure of is that it's calling the right equals operator. Because and the order matters here. Because I think this is just a hunch. Let me see if it's true. I think if we reverse the arguments and we said min frequency of 0 dot least common equals f dot call of frequency, I think this will fail. Let's see if I'm right. Oh, that worked. Why did that work? Huh? So my theory is that this first argument is used to determine what comparison method you actually run. And so it would need to be defined from both sides. So I want to see the type of min frequency. Oh, it's an integer. Interesting. So the Python parser must do it from both sides then, because I can guarantee you that integer does not have a defined equality operator with the Spark column type. So if you look at the type of, whatever the f dot call returns, it's going to be a Spark column. Yeah, so this is a Spark column. So I can guarantee you that int does not know how to compare itself to Spark column, but Spark column knows how to compare itself to int. So there must be some bidirectional thing going on in Spark where it tries both or something.
Find out what type of data stored.
In this column, let's see. There might just be like a data type. Let's see what functions it has. Anything that looks like type here? I don't see anything. Not from this, at least. You could always look at the schema for the table. So if you want to know the type, then, whoa, you could do Spark table. And that will give us the schema. Or if you wanted to pretty print it, you could say print schema. Okay. So this has a column, new word, which is a string, and frequency, which is a long or 64-bit integer. Okay. So this.
You kind of compare the reduced frequency with the string. That's when some sort of.
If you wanted to compare your least frequency with a string,
If you put your other column instead of it's the least common. What we can get. Maybe we can
oh, I deleted it.
get. I assume that.
Yeah, so you can only compare, two things that are of compatible types to be compared. And Spark will check that for you. So if you try to compare like a string column and an integer column, that's not going to get you anywhere. So we could try that. Dot is there an equality operator between must be? That's interesting. So it looks like Spark has an equality already defined between strings and integers. Some SQL engines do have that. So like Snowflake will do that. Snowflake, if you compare like an integer column and a string column, you will it will automatically cast one to the other and do the comparison. But if you do that in Python, that's not going to get you any. Let's say 9, 9. That should seriously? When did this happen? This did not used to be a thing. I remember. Is it the plus operator that it can't figure out? Yeah, that's what it was. Okay. So it doesn't automatically cast for everything, but it does automatically cast for some things, which is odd. Okay. That may have been confusing.
Well, but if you don't know, you don't know you've been checking it, so you're carrying the thing, people see the errors, but you know, yeah. Information over here, behind community.
Yeah. So I like to rely on type checking to make sure I'm not doing anything stupid. And in this case, that might not necessarily be a bad thing to just automatically cast um, integers to strings in order to do the comparison. But in other contexts, that might be not good. I wonder if that works on a join. Now I'm curious. Let's see if that works on a join. Let's see if we get a type error when we try to join them. When we try to use it as a join key. That would be crazy. And what we're going to do is, actually, I'm going to give these two things different names. Um, so it's going to compare the frequency from this to the word from this, and it's going to join on that. And this is not going to come up with any rows because we stripped out numbers earlier from the new words data set. But I want to see if this even like runs properly, and a Spark will let you do this. That's nuts. This should not come up with any rows. Look at that. You can use it as a join key too. Interesting. I did not know that. I'm learning too here. Okay. Where were we? All right. So what happens when, let's say, we want to find the um, maximum length or maximum total length of the words within a particular line? So we can't just go back to the original data set and try and find the length of the line there because we have to strip out things like white space and punctuation. So I want the total length of all of the words in the line, but not the length of the line. How would I do that? I want the total length of all of the words in a line. Yes, I want to add the words. I want to add the lengths of the words together to see what the longest line is in terms of the length of the words in that line. I want to exclude all the white space and all the punctuation. Let's go back to the original. So there are a bunch of different ways we can do this.
without on the white space. And all of you, oh, or is it all in one channel right now? And is it all in one right now? I can't remember your.
Okay, yeah. So if so yeah, right now it's all in this table, it's still raw.
Okay, so that's still a regular, a line, a regular line. That's a row with a line.
Yes,
Okay.
that's one record.
Divided.
Yeah, so it's divided into lines right now, and the way to do this could be really easy. So we could say, we could add a length column. Total word length. And we would define that as something like f dot. We could replace all the things that we want to strip out with the empty string. So we could replace white space with the empty string and punctuation with the empty string. And what we wind up doing is we could say regular expression, replace, and I forget the syntax because I always forget the syntax. Okay. String containing regular expression pattern. And so what we would need is a column, which is just value, and that's right. And so let's say anything that isn't A to Z uppercase or A to Z lowercase, we're going to strip those out. And then we're just going to replace it with the empty string, and that should be all. Nope, wait, we need the length. F dot. Right, let's see where that gets us. Okay, so that gives us the total word length. That is 12 words. That is that 12 letters? No, that's 11 letters plus 7 plus 2, which is 20. So it's excluding the white space, which is good. That's exactly what you want. What if we wanted to make this a little harder? What if I would say, show me the total length in a lot for each line of all the words that start with A. So we need to divide them into words first. We already did this earlier. So let's say, yeah, words. So we already did the work to split them into words. So we can split them into words. Now what do we do? We still have to strip the columns. Well, we still have to strip the words, right? So we have to do that. And we have to filter the words to see which ones start with A. So where do we want to start? So maybe what we should do first is we can expand all the words into one, or the words column. What's the problem with this, with doing it this way? Because we want the total length of all the words to start with A per line. But we've lost our lines. We don't know which line this word used to be a part of. And so something nice that Spark allows us to do is you can add a row ID as a column. So it has a function for that. So Spark has a with column. We're going to call it row ID. And that function is called monotonically increasing ID, which is very creative. But I've used this function before, and it's really nice because this is extremely efficient. This is only a 64-bit integer, and what it does is, we're going to talk about this later, but Spark data frames are separated into partitions, and each partition itself also has an identifier. So what it does is the first half of this ID is going to be the partition ID of the original row, and the second half is the row number within that partition. So it's very nice. So we can generate our row ID, so we can join it back. Okay. So let's see where we're at right now. Okay. So as you can see, we have, kind of everything separated by row ID, which is good. So now what we have to do is we have to normalize the words in the same way that we did last time. So let's just transform the word. Okay, now let's see what that looks like. Okay, so now what do we do? Well, we gotta do one other thing first. We gotta filter out all the things that don't start with A. Yes, we gotta filter first. It's F dot starts with word, and we have to use F dot lit this time too. And that could get us somewhere interesting. Okay. All right. So it looks like this will not be just one word, which is nice. Okay, so now what do we do? Group by word?
By row ID.
Yeah, so we gotta group by row ID and join it back on the original rows. And then once we do that, so we're counting the total character length of all the words that start with A within a particular line. So yeah, so we want to sum them length of the word. And that will give us total A length. Look at that. Now, what if I told you there was a way to do this without using explode and a row ID and another aggregate again? We could just do this entirely row-wise if we wanted to. Here's a hint, there's some functional programming involved. And this is a more efficient way to do it because we wouldn't have to do this group by, because the group by involves a data shuffle, which is moving the data between machines. This other method with functional programming doesn't involve shuffling at all.
So if we had a function that takes in a value and already and then it filters out. And we filters out everything except our words that are there and comes then. And if we choose that, then we could suck.
Yeah.
No,
Yes. One way we could do this, the easiest way to do this is we could use a UDF. So we could define a specific Python function that takes in an entire line, and then within that UDF, splits them up. So split a, or let's just call it a length. And then just call this line. So then what we do first is we would have to split every line. I forget how to do a Python split. Yeah, line dot split, but we want to split on a pattern, not just a separator. Stop. This is not what I'm looking for. Split all white space. Why is it not submitting it? Oh, does it just do this by default? That's nice. Okay, so first we need to do line split. Let's do dot trim first, because I've seen Python split do weird things. Let's actually check that out. If it starts with a string, split, what does that give us? Oh, okay, so we don't need the trim. Trim dot split, and then actually what we should do first is we want it all to be lowercase. Does that matter? Yeah, so we don't have to do a comparison. And then what we can do is we can honestly just do the stream. E replace. That's a moment. Okay. Import expression. And we would do e dot sub. It's just going to be that. Okay. Replacement. Oh, we want this and string. And then what we do is we could say length or return length of words or with that starts with. Okay. And then in order to actually make it a UDF, we have to either create a UDF object or register it with Python SQL. Feel free to chime in with a question while I'm writing code if you want. Oh, that's funny. That's not what we want. That's what we want. So then we can say, geez, I never remember how to do this. Seriously? Okay, look at that. So we've got spark.sql.register, and then we're going to call this a lengths, and we're going to use a lengths, and the return type is just going to be a long. So a 64-bit integer, which honestly isn't necessary. So let's just do that. Because let's be honest, none of these strings are going to be over 4 gigabytes. There's no attribute register. Oh, yeah, it is. Okay, there we go. So now we have it registered. We can go back to what we were trying to do originally, and we can say with column. We can say total A length. And that's going to be once of the string. Let's see where that gets us. Look at that. And it looks like it works. So we have the total length of everything that starts with A, which is just this initial and the word and that's fine. None of these have anything that starts with A. That's just and. This is just at. Looks good to me. Okay. No, so there's only one column in here, and the column is called value.
So echo expression. What is the expression? You need those of that same yeah.
So the expression is a little bit weird. So it allows you to mix SQL syntax and Python syntax in the same Spark declaration. So what this is doing is we don't actually have a reference to the Spark UDF outside of SQL syntax because we registered it as a UDF this way. If we created a UDF object instead, then we would be able to use it as like f dot anything else. So we can create it in 2 different ways. I still forget how to do this every time. I want to create a UDF object. Okay, so we can also say a lengths UDF f dot UDF, and we pass in a lengths. And we also say that this returns an integer type. Place to previously register function. I don't care. We didn't change it. Okay. So we could declare this in the same way. We could just say a lengths UDF of value. And this would do exactly the same thing as f dot expression. The reason f dot expression is nice is because sometimes I usually like to declare everything in Python, but occasionally the Python syntax gets a little bit too verbose. So f dot expression can kind of mitigate that a little bit because the SQL syntax tends to be terser in some places, but not in others. Does that make sense?
Okay, so the F1 expression, not SQL syntax, so it's a string, but it parses that out, and there's a SQL, that string, they know that is a column name inside there.
Yes.
Okay, what if I am passing multiple columns, so I can still just within this string, I can column.
Yep.
It would,
And just for funsies, let's add the same thing twice. Well, that was not supposed to happen. Let's add the same thing twice. Line copy. The line copy is not going to do anything, but you can still use it because it's fun. So now I should just. Is that properly aligned? Okay. So now it's probably going to give us an error because, all right, we're missing a positional argument, which is exactly what we would expect. Let's just pass the value in twice, or literally anything else. It can be this string literal, and it still gives us what we want. So you can have any number of arguments to these UDFs that you're creating. And these are the two different ways you can create your UDFs. You can register them, so then you can reference them from within SQL syntax, and you can create a UDF object, so you can use them outside of the SQL syntax. So those are two different ways you can declare and use UDFs. Questions? Okay. So let's just check this out. All right. So the interesting thing is that let's say we don't want to use a UDF. Let's say that because UDFs are slow in comparison to Python's built-in functionality. So the reason why, especially Python UDFs, are so slow is because when you introduce a Python UDF to Spark, this becomes what's called a polyglot application, where you have two different languages that are running code at the same time. So in order to run this Python code, what Spark has to do, because Spark is written in Java and Spark runs on JVMs everywhere. So what it has to do is every executor and every core has to create a separate Python process, take all of your rows, send the data to Python, like through inter-process communication, which means it has to serialize it, send it over. Python has to deserialize it, and then it's able to use it in the Python code and run the Python code. And then when you return from the UDF, so we're returning this sum, or we're returning this sum, which is just a number. It has to serialize the number and send it back over to Java so that Spark can actually receive it and then do whatever else it needs to do with it. So there's this huge overhead to the communication between Spark and Java, or between Spark and Python, because Spark runs in Java, but we're writing code that runs in Python. And that overhead makes Python UDFs way, way slower than using Spark's built-in functionality. So there is a way to do this row-wise without doing any aggregations and without using UDFs. And that's because Python's row-wise functions for collections are actually extremely powerful. So we can manipulate these PySpark collections and the functions available to them to achieve this functionality without having to use any UDFs or aggregation. And this is how you achieve performance in Spark. There was one time I was working with a data scientist. We were developing a score to see, how related people are. So, if you're using, a family member's credit card versus you using some other random person's credit card, one of them is way more likely to be you committing fraud. If you're using somebody some other random person's credit card, that's way more likely to be fraud than, you're using your spouse's credit card or maybe your parents or your sisters or whatever. So what we did for this was we wanted to create a score to see how likely it is that two people actually know each other. And the original function was a UDF written in Python. It was, 35-ish lines of code. And it ran reasonably quickly. So it took about 20 minutes on this 1 million line sample. And I looked at this function and it took me probably 15 minutes of reading this function to figure this out. Where I'm like, you can actually implement this entirely in Spark without any UDFs whatsoever. And so I changed it to be admittedly a fairly complex, but single line of only built-in PySpark or only built-in Spark. And that took it from running in about 20 minutes to running in 2 minutes. So it was 10 times faster because we took out the UDF and we replaced it with Spark only materials. So how do we do this in Spark and only in Spark? So how I would start off is about the same as what we started off doing here, which is we'll split the column into words, but that's where things get a little bit different. So then what we do, also, by the way, you can use this other method called select expression that does exactly the same thing that select does, except it uses the expression syntax that f.expr uses, which is nice. So it's kind of shorthand. So let's see what we can do. We can do exactly the same thing that we did in this UDF, but instead do it in native Python or native Spark. So let's break this down. So what we want is we want everything to be lowercase. And honestly, what we should do is we should do f.lower first. So everything's lowercase before we split it. That makes things a little bit easier. And then what we want to do is we want to say we're going to strip everything out. So how would we strip all of these words? So if we go and look at our list of functions, this is too long. Okay. So if we look at our list of functions that are available to us, you'll see these collection functions. And these collection functions are pretty powerful. And they allow you to do a lot with very, very little. And so we have this transform function, which is exactly like map in other languages, but it's called transform here. And you have filter, which is exactly like how filter works on data frames, but instead it filters individual elements of an array call. And you pass it a function to define what you want to filter out. So it works the same way as that. You can use aggregate, which is the same thing as fold that we talked about in the functional programming lecture, where it defines your initial state and you can accumulate and modify the initial state to produce one result after that. So we're going to use a combination of all of these things on array columns. So let's see what we got here. First, what we want to do is we want to do a transform because we want to strip out all of the punctuation from everything. So we'll do a transform. And we are transforming the words column. And we will do a regular expression, replace this thing. Should replace. Oh, this is an anonymous function, by the way. You can declare anonymous functions in Spark SQL, which is pretty cool. Okay. So let's actually go through this one by one. So we're going to continually overwrite the column, and we're going to go through this step by step because this gets slightly complicated. Words. F.expr. Okay. So now what we've done is just to show what's going on so far. We don't need 100. Script. Okay, now we can see the difference. So now we can see the original. Oh, this has all three. Let's drop the original column. Okay. So we have these things lowercase and stripped now. So that's the first step. Now what we're going to have is, I'm actually going to expand this outward because these chains can get rather long. So now we're going to have with column. All right, what's the next step? So we have everything stripped. Now we need to filter out everything that starts with A or that doesn't start with A, right? Okay. So A words, F dot expression. So it would be filter, which is different from the data frame filter. This one filters individual array elements in an array, but it works the same way. So we're going to filter the stripped column, and we're going to use this function, this anonymous function, and it will be starts with X, and that starts with A, then that's what we want to use. How do you print vertically in Spark? I forgot. Huh?
The show only shows that they're there.
Oh, okay. Okay, there we go. Okay, so that's exactly what we want. That's what we want to do. And lastly, we want the total length of all the A words. A word length. And what that's going to use is it's going to be, what was this function called again? Aggregate. It's not called fold. Aggregate, and we will look at the initial value. We first need to look at A words. The initial value is going to be 0. The merge is going to be, forget the syntax, X comma Y. Is that what it is? And it's going to be X plus length of Y. The Y in this instance being the string. And that should be all we need. Let's see how that works. All right, look at that. So what this does is the first transform takes all the words and strips out the punctuation. The second is the filter that takes the stripped words and filters out everything that doesn't start with A. And the third is the aggregate that takes all the words that do start with A. And, we have this initial state, which is 0. And then for every single member in this A words array, we call this function. The first argument of this function is the cumulative value, which for now is 0. We add the cumulative value to the length of the word that we're currently processing. So what the cumulative value looks like is, at first it starts at 0, and then the first arguments to this function are going to be 0 and the word A. And then it's going to return 1, because 0 plus the length of A is 1. And then the second time around, the cumulative value is going to be 1, because we already processed A. And then the second time we call this, the arguments are going to be 1 and the word and. Then once we process, once we go into this function, it's going to be 1 plus the length of the word and, which is 3, and that makes 4. And so now that the array is done, the entire thing returns 4. Yes. The aggregate, it can be anything. So we could even multiply it if we wanted to. We could do whatever we want. We could switch the order or anything. This body can contain whatever you want, as long as it produces a value of the same type as the initial value.
That actually goes to accumulated. Whatever your first is.
Yeah, the first is the accumulated value. The second is the value you're going to add to the accumulated value. So this is what functional programming looks like, and this is why we spent an hour talking about functional programming 2 weeks ago. Is you can do this kind of thing and write incredibly efficient code, even if it looks a little weird. So this is going to be much, much faster than either the UDF solution. The UDF solution is going to be faster than the aggregate solution that we talked about earlier, using monotonically increasing ID and group by.
Record, it's faster than anything on a right. I mean, it's still is doing that, but it's doing it per record, so it's converting to the right and per
Yes.
row.
Yes, it's doing it per row. There's no shuffling going on. That's what makes this more efficient.
Oh, when you aggregate across the data frame, you might have to be switching.
Yes. Yes. So you might have to transfer data between cores or between machines when you aggregate over the entire data frame. But when you aggregate within a single row, then you can do everything completely in parallel, and you don't have to do any communication between machines. That's why it's so much faster. That's all. Are there any questions? It's a fun time, isn't it? And yes, I have used techniques like this to make my code run not slow. It's not how my head works either. I had to learn how to do this.
Go back and functional programming and more fun. It's not.
Yes, I agree with you.
It's a lot.
Yeah, so I'm planning on putting together like a Git repository with everything in there. And I'm going to have some written instructions on how to start and manage EMR clusters and all that stuff. So I'll have published all that stuff before you all get your first assignment.
Thank you.